I'm sure you've studied transformations in middle school. We may not have called them this. You may have said flips or slides or turns instead of these words, but I'm sure you studied moving things around on a graph, right? Okay. And what we're going to do today is talk specifically about mathematically how we write that. And this is actually one of the quickest and biggest, fastest growing areas of mathematics because it's exactly how Pixar works. You know, Pixar, like Finding Nemo and Cars and all that. Down to its basic level, this is what Pixar animators do. They type in the directions to move a shape on a graph like this, to the left, to the right, up, down, flip it back, upside down, do whatever. They're typing in directions into the computer, and that's making the pixels that make up Nemo or whatever, like all those pixels are then moving together. So it's probably a really applicable area. Yeah.
So is that what like movies take like 10 years to completely finish?
Yeah. Yeah. There's a lot of, and you know, originally I think it's getting faster, but originally they would type in the directions and see how it looked, and then they might have to go back and type in something else because they didn't like it didn't look exactly right. You know how like if you go back and see the very first Pixar movie, it doesn't look as real as like Toy Story 3. You know, so they're getting better at it. But anyway, so let's talk about the nomenclature, like how to label things, what we call things. The the image we start with, okay, whatever shape was on the graph first, the one we're going to move, we call that the pre-image. Okay, then the one that ends up where we wanted it to move, that's the image. So the first one, the one we start with, is the pre-image. The one we end up with is the image. Okay? And the original image, the pre-image we start with, is just labeled by its vertices with regular letters like W, X, Y, Z. Okay? The result, this little arrow, this is arrow notation, and it stands for is transformed into, because we're doing transformation. So this says WXYZ is transformed into, and these little tick mark things here are called prime marks. And we would say this W prime, X prime, Y prime, Z prime. All right, so to read this across, WXYZ is transformed into W prime, X prime, Y prime, Z prime. And that's how we mark the image, the new placement of the image. All right. So if you look at this, let me make it maybe a little bigger so people in the back can see. If you're looking at this, did this shape move right and down or left and up? How many people say right and down? How many people say left and up? Okay. How do we know which one we started with? Yeah, the one without the little prime marks. So this was our first shape. And this, because this one has all those little prime marks, that's our second. That's the result. So it went right and down. Make sense? So far, so good? Yeah? We're all just saying that. Okay. All right. So let's do some specifics here. All right. So a translation occurs when you probably talked about that as a slide in middle school. It happens when the shape does not change. It doesn't get bigger or smaller. It stays exactly the same measurements, and it doesn't change the way it's oriented. Okay, so if the hypotenuse of this right triangle is facing left, in a translation it would be facing left the whole time. Okay, so a translation just takes the shape exactly as it is and just slides it around the graph. Okay? And to show that, we're going to learn what we call transformation notation. Okay? And I think the best way to do it is to actually show you like how the points change. So if I write all the points on the pre-image. That's A, B, and C. Okay? Anna, you're close. Can you read the ordered pairs for A, B, and C?
A is -3, 7,
7. Okay.
and then B -3, 2. C is 7, -2. No, 7, 2. -6.
Yeah. -7, 2. Okay. So that's the pre-image. That's what we're starting with. The image then would be A prime, B prime, C prime, right? And those points, would that be the one on the right or the one below? The one on the right, exactly, because it's the A prime, B prime, C prime. So the A prime, I'm just going to write them off because it's hard to see, I know. The A prime is 3, 7, 3, 2, and -1, 2. Okay. Now, take a look at those points, and don't think about it moving on the graph, but think about it mathematically. How do we change these coordinates into these coordinates mathematically, like adding, subtracting, multiplying, dividing? How do we change them? Take a second. You take x and add 6. So she's saying -3 plus 6 is 3, -3 plus 6 is 3, -7 plus 6 is -1, so that works. So we're going to add 6. How about to the y's?
Stay the same.
Yeah, they just stay the same, right? 7, 2, 2. Stay the same. So nothing happens. All right, so what would a Pixar programmer enter into the computer to tell all the points? Now, we have a very simple triangle. Think about how boring the movie would be if that was the main character, right? There's 3 points. So if that was the main character, this triangle, you know, I'm not sure what the storyline would be. So we are doing this with X and Y, but picture when they do it, they're doing it with millions of points at once. Okay, we're just doing it with 3 points. Does that make sense? Okay, so what we do is we say take all the X's and Y's that we have associated with this shape. So that point, that point, that point, but also that point, that point, that point, that point, that point. Like every X and Y on that shape. Okay? Transform it. Remember that arrow means transform it by, and this is the place where they tell it what to do. How do I move my shape? Okay? So I take X and do what with it? Add 6. And then Y, what do I do to that? Nothing. So I just leave it. Why? So this is called transformation notation. Okay? It tells what we're looking at, and this part is important. I mean, it's always going to be X and Y for us right now, but it gets important later when you like graph in 3 dimensions, because then it'd be X, Y, and Z. And so there are other choices. For us, it's always going to be X, Y, but there are others, just so you know that. Yes? Yeah, absolutely. Okay, so now this shape, when you think about those movies, they move constantly, right? So we moved it from the pre-image to the image. Now let's make this one the pre-image and this one the image. See, this is A prime, B prime, C prime. This is A double prime, B double prime, C double prime. And if we moved again, what will we call it? A triple prime, B triple prime, C triple prime, right? So see if you can come up with the transformation notation for the move from A prime, which is the pre-image now, to A double prime, which is the image. All right, so how did those change from A prime to A double prime? Ella?
I said stay the same.
So you had X, comma Y, transforms into?
Yeah, I had X staying the same.
Mm-hmm.
Y minus A.
Good. Some people had that. Good. All right, so that's a translation. That's when things just move around. Now, it won't always be that X, if Y changes, X could also change. Like you could have x plus 1, y minus 8. You know, they could both be moving at the same time. All right, reflections, or you might call them flips, are when the shape stays, the measurements stay the same, so it stays the same width, same height, but the orientation switches, and it's a mirror image across an axis. So is this shape, it's reflected across what axis? The y-axis, good. And this one is reflecting across x-axis. Okay, so let's see if we can come up with how to show that in uh, transformation notation. So again, we have A, B, and C. We know that A is negative 3, 7, B is negative 3, 2, and C is negative 7, 2. And A prime, so that's the pre-image. The image of A prime is at 1, 2, 3, 7, 3, 2, and 7, 2. Okay? What's happening there? Think about mathematically. Take a second. Okay? So the x's they went from a negative to a positive, and the way you do that, the way you change a sign of anything is you multiply by negative 1. So I would write x comma y is transformed by, and how would I write that? Anybody have an idea? How do I show that you multiply the, right, negative 1 times x. And the y stay the same. Okay? And doesn't that kind of make sense? Look at the picture. This is the y-axis. So is the level of the y changing? No. But look, if this is the x-axis, the x's are going from here over to there. So the x's are changing, even though we're reflecting across the y-axis, it's the x's that are changing. Okay, sometimes I think that seems counterintuitive, but even though we're reflecting across the y-axis, it's the x's that are changing. All right, so see if you can come up with the transformation notation for this flip. If this is the pre-image, what's the reflection here for the image? Notation look like? So be x comma y transforms. Right, x comma negative y. Good. Now there is one other kind of reflection, and you will see this. I probably wouldn't ask you to write the transformation notation for it, but you would see it on the paper. Sometimes this is the y equals x line. Goes exactly up through the middle. And sometimes you'll see reflections across that y equals x line. Okay? So just be aware of that. It could still be a reflection across that line instead of one of the axes. So the pre-image is rotating clockwise or counterclockwise? Clockwise. And then how many degrees from here to there? Does it look like it's close to 90, but it's past it, right? What do you think?
Oh no, because of the arrow.
Yeah, the arrow shows that, but it's, yeah, if there was no arrow, you could go that way. Yeah. Generally speaking, we always count the shortest distance as the way it's rotating. You know what I mean? If we have to go past 180, chances are you're supposed to go the other way. Does that make sense? Okay. So it's about, if you think about 120, about a third of the way around the clock. So it's rotating clockwise 120 degrees, And the other thing you have to identify is the center of rotation. And that is basically, where did I stick the pin that everything is spinning around. Okay? So in this case, it's right on the axis here. And so here's a point it's spinning, and it's going around like that. Okay? This one, which way is it going? Clockwise. How many degrees? Almost 90, right? It's going from here. If it was all the way down to there, it would be 90, but it's maybe like 85. So it's going clockwise about 85 degrees. Now this is the tricky part. For the center of rotation, the center of rotation is outside the shape. And you can kind of tell when these don't touch. Like, see how these are always going to be in contact from that center point, but these don't touch. So the center of rotation is out here, and then can you kind of picture having it attached to like a little string and then dragging it around? Does that make sense? It's that little distance too that's moving. So the center of rotation is outside the shape. Okay? And sometimes it's just square in the middle and it just spins around itself. So like if it were a square where the center of rotation was right in the center, every 90 degrees you wouldn't even be able to tell it moved. Right? Because it'd be right back where it started. Okay? All right, let's take a look at some of these and see if you can tell me what kind of transformation we got going here.